Okay, so it's 11 o'clock, so let's just get it started. First, there's some. Okay, first, welcome everybody for being here and also online. And today we are going to have two speakers. Don't get scared, it's only 1 hour. So the first speaker is Tong Lee, who was actually a PhD student at local here WePax group, and he got his PhD just later this spring, and now he starts his postdoc position at Lawrence Livermore National Lab. And the second speaker is Mookyong, right? And he's a student, a PhD student right now at the statistics department at SU. So his advisor has two advisors. One is CAPS, and second one is Shujita. And yeah, please go ahead.
Yeah, thanks for your introduction, Celine, and I'm glad to be back in just several months after my graduation and talk about my research work with my many collaborators here at MSU. But before I start, I just want to make an advertisement because the nuclear data and the theory group at Lawrence Livermore National Lab is going to recruit several postdocs soon. They are still going through the administrative process, but I think it will be announced soon. So just stay tuned, and I think the AFRI Theory Alliance mail list will also announce it. Okay, diving into the research. So today I'm going to talk about my research on the parameter calibration for beta-decay calculations with the Skyrme finite amplitude method. Here the calibration will be is done by two methods. One is the what we are familiar with is the chi-square optimization, and the other is the Bayesian model calibration. And the Bayesian model calibration will be mainly discussed by my joint speaker Mookyong. And but before that, I will start from the physics. Yeah. Yeah. So this research work is mainly focused on the beta-decay calculations, which has some kind of roots in the study of nuclear synthesis, especially the R-process studies. We know R-process studies, the rapid neutron capture process produces lots of elements in the universe. And in this process, the beta-decay is a strong competitor against this neutron capture process. And it tends to bring the nuclei back to the value of stability. Since this R process traverses through the neutron-rich region, which experiments have not had access yet, the theoretical predictions of these beta-decay rates are crucial to study the R process. And also for this theoretical study, we need some kind of tool that can conduct global calculations throughout the nuclear landscape. So in this sense, the nuclear density functional theory, nuclear DFT, is a good choice to do this work, as it does not involve that much computation, but it's still a microscopic self-consistent method. And in this framework, we need to do model calibrations and uncertainty quantifications to provide reliable beta-decay rates for the R process studies, and that's the main topic for today's talk. So just some brief introduction for the nuclear DFT. In this framework, I think I step on the line and then it breaks down.
Did you press some button? Wait, did you step here?
Yeah. Okay.
Oh, okay.
Yeah.
That line. Great. Don't just step on it. Maybe. Okay.
You found out the source of the problem.
That's great. Yeah. This. I feel that I'm limited. Okay, so in this framework, the energy of the nuclear system is approximately expressed as a functional of various local densities, including some time-even densities or time-odd densities, and also we have also the pairing effect included. And this, and then based on this, the energy density functional, the self-consistent hyperfocal people equations are solved to describe the ground state of even nuclei. And the code we are using is HIBTHO, which solves the system in axially deformed common oscillator basis with time reversal symmetry. And based on the HIB solution, we need to describe the Beta-Decay transition, and which can be obtained through the quasi-particle random phase approximation, QRPA. The main problem is that the QRPA equation is numerically difficult to solve, and because of the huge dimension of the matrix, we need to diagonalize. And recently, the finite amplitude method, the FAM, has been developed to provide an efficient approach to overcome the difficulty and makes the global calculation over the whole nuclear landscape feasible. So for the finite amplitude method, it assumes that our system is under a periodic external perturbation like this. Here, beta and beta-dagger are quasi-particle annihilation and creation operators. And then we assume that those operators also oscillate, have some kind of periodic oscillation. And then we can put all these things into the time-dependent hyperfocal Gribov equation and finally obtain the so-called linear response equation, which describes the response of the system in the linear approximation. Here, this A, B, B star is the QRPA matrix. And if we need to explicitly construct this matrix, it will basically go back to the QRPA problem. But in the FAM, we do not explicitly construct the matrix. Instead, the matrix vector product here is done implicitly. So that we do not demand that much memory, and the computation can be done in a very quick way. So in this equation, a complex number value for this omega, which is the oscillating frequency, is usually utilized. So the imaginary part will place the role of a smearing strength in the strength transition strength function. And what this is. And for the Beta-Decay problem, this external field will be constructed with the one-body Beta-Decay transition operators, which is it's also known as the charge changing operator. And in our work, both allowed and first forbidden transitions are included. So the FAM program we are using is called the pnFAM, proton-neutron FAM, and it's basically developed by our collaborators at University of North Carolina, and it has been used for global beta-decay studies for both even nuclei, odd A and odd nuclei. So based on the FAM solution X and Y, we can calculate the observables we want that we can compare with the experiments. So the FAM strength function is calculated by some kind of inner product between the external field and the FAM solution XY, and it is shown to be some kind of in this form where these matrix elements are divided. Transition matrix, square transition matrix elements are divided by this omega minus the QRP energy capital omega. So we can see that so this response function is this is an example of the response function for the Gamow-Teller transition operator, and to get the Gamow-Teller transition Gamow-Teller resonance, we can do the calculation do the FAM calculation along a line horizontal in the complex horizontal to the parallel to the horizontal axis, like this, omega equals capital E plus I gamma, where this fixed gamma is kind of like is a smearing width, and if we do this kind of calculation, we can get this kind of response function, and then we can interpolate the response function along this line and find the maximum position, which is the Gamow-Teller resonance position. So for the beta-decay half-life, I think it's a little bit complicated, but as we see in the previous slide, this kind of the square transition matrix elements are kind of like the residual for the at those QRP energy capital omega. So then we can use the a contour integration in the complex plane to extract all the contributions from all these poles residuals, and then get the beta-decay transition rate. It should be noted that this and the integration, the response function should be weighted by the phase space factor that describes the leptonic kinematics, and the contour should include all the poles that have positive Q values and contribute to our beta-decay transition rate. So now let's turn to the calibration, model calibration we did. So the Skyrme parameterization unit F1-HFB is employed in this work, and the time-even Skyrme couplings have been heavily calibrated in this functional. And in the pnFAM calculation, time reversal symmetry is broken, as we have seen that it's based on the time-dependent HFB equation. So this kind of we need to calibrate some time-out Skyrme couplings. Here we try to calibrate this CS and the CT, while other parameters we are determined by through the gauge invariance that like some are equals to some other time-even parameters. Some time-out Skyrme couplings are zero to avoid some instability, things like that. So, but in the calibration, usually it's better to use some dimensionless parameters. And so in this case, we use the lambda micro parameters Z0 prime and Z1 prime, which are connected with those CS and CT Skyrme couplings. What we know is that some experiments on the Gamow-Teller resonance measurement give us some kind of Z0 prime value around 1.6. Well, it should be noted that there are kind of different normalization conventions. So you may see some different numbers in some papers, but just make sure you get the same normalization. So the other part is the pairing part, which we use the density-dependent delta interaction, which in this interaction we have both isoscalar pairing with naught and the axial-vector pairing with 1. The axial-scalar pairing is needed to be calibrated. It needs to be calibrated, while the axial-vector pairing is taken as the average of the proton-proton, neutron-neutron pairing strengths. So to make things dimensionless here, we just divide this use this dimensionless small v naught, which is the axial pairing strength normalized by the axial-vector pairing strengths. And the last parameter is the effective axial-vector coupling, which describes the quenching effect in the Beta-Decay. As many literatures has pointed out, this quenching effect is mainly attributed to the so-called two-body current. And work on the two-body currents, there are already some results for the inclusion of the two-body currents in the Skyrme pnFAM. But now it mainly focuses on the Gamow-Teller transition. And in the future, we hope that if it's extended to the forbidden transitions, we can remove this axial-vector coupling from the calibration and instead try to calibrate the parameters included in this two-body currents. So I should mention that the previous pnFAM work without the two-body currents included employed empirical value of this axial-vector coupling at 1.0. And this is our starting point for the calibration. This value looks okay for many existing global calculations done with the pnFAM. So there is also an interesting physical problem with when we try to vary this isoscalar pairing strength. We see some kind of abrupt change when this isoscalar pairing becomes quite strong. This is kind of the rate of the argon 48 at different values of Z0 prime and V naught. And we see that the function become kind of incontinuous here at around V naught equals -2. And the reason is the QRPA instability. As we increase the isoscalar pairing strength, some pole can move out of the contour we use for the integration and onto the imaginary axis, and then it will lead to this abrupt change. Because with the strong isoscalar pairing, our original HIB solution is no longer a minimum, as the isoscalar pairing is now taken into account in the HIB method. So this is causing the instability, and the range of our isoscalar pairing strength should be constrained. It cannot be very strong. And this also shows that this kind of rate can be some kind of not smooth. So this will also impact our choice for some Gaussian process kernel in the later Mookyong will discuss later. So for the experimental data, we use the locations of Gamow-Teller resonances, with some selected doubly magic and semi-magic nuclei, and also we use the Beta-Decay half-life data given in previous pnFAM studies, and we see that this figure shows the logarithmic of this half-life, and we see that it spans quite several orders of magnitudes, and in the calibration, the logarithmic values are used. So this is kind of a brief framework for the numerical framework that we developed to do the model calibration. Both HIV teacher and pnFAM are underlying physics programs written in Fortran, and then calculations are managed by a Python wrapper called pnFAM, and then this pnFAM is again wrapped to give inputs for the chi-square optimization routine, and also data generation for emulators, which can be used for Bayesian model calibration. So now for the calibration part, let's look at the chi-square optimization first, which gives us some kind of deterministic results that can guide us further in the following Bayesian model calibration. So the quantity we need to minimize is the chi-square, which is the weighted sum of squared errors. This epsilon is the weighted error or residue, and it's kind of the difference between the between our program's output and the experimental value, normalized by some weight W, and then it's divided by this degrees of freedom, which is the difference between the number of data points and the number of parameters to calibrate. And in this case, we also use the convention that weights for points of the same observable type are the same. We have two types of observables, Gamow-Teller resonances and Beta-Decay half-lives. So we have basically two ways to determine. And in the from the practical perspective, we use the ponders developed by the Argonne National Lab to do the chi-square optimization. The basic idea, the advantage of ponders is that it does not require any derivative information. Instead, it tries to form a quadratic model based on already obtained results already obtained, and it has already been well utilized for the basal unit functionals. So in the chi-square optimization, the main assumption, statistical assumption, is that our weighted residues are independently Gaussian distributed with the same variance. So then, based on that, the probability distribution of our parameters can be written as the exponential to the minus chi-square over this 2 sigma squared, which we can then do a Taylor expansion on this chi-square to obtain this approximate this equation, where this H is the Hessian matrix and X hat is the optimal parameter value. So then, based on this expansion, we can derive the approximate formula for the covariance matrix, which involves this matrix G, which is the derivative of our weighted residual epsilon over the parameter X. And then, based on the covariance matrix, I can also obtain the correlation matrix. This variance is the diagonal elements on this covariance matrix. So since we have two different types of data, we need to first determine the weight that we need to use for the normalization. We see that with only one type of data, some parameters cannot be well constrained, and it's quite necessary to include both types of data. And actually, only the relative weight matters, because we can always do some global scaling on this chi-square. I scale them to 1, and then the corresponding weight is also scaled. So there are quite a lot of factors to take into consideration for the weight determination. Like at least 3 main considerations. We take first, the weight should be close to the root mean square error of that, because of our assumption that our weighted residuals follow the same Gaussian independent Gaussian distribution. And consideration 2 is that our scaled weight should not be too small than the typical experimental of that observable time. And also, we want to kind of balance the errors of different types. We do not want one type of data have really very large errors. Sometimes, actually, these considerations sometimes contradict each other. So it's kind of quite a subjective issue, and we carry out a series of optimizations with the fixed weight on the Beta-Decay half-life, and also vary the weight for the GPR data, and then we finally choose these weights based on those 3 considerations. So now this table shows the optimization, the optimal parameter values we obtained after for the chi-square optimization, and we have 4 different optimization schemes. In A and B, this G1 prime, which is the Skyrme, which is related to the tensor term in the Skyrme parameterization, is fixed at 0, assuming no tensor term. And in C and D, G1 prime is free parameter. And in AC, this axial-vector coupling is fixed at the empirical value 1, while in B and D, GA is again free parameters. And we see that when we have these values are optimal parameter values, and the values in the brackets are the standard deviation. We see that when we have this tensor term G1 prime included, both G0 prime and G1 prime are not well constrained. They have the standard deviation of G0 prime becomes quite large, and then when both G1 prime and GA are free, this G0 prime are pushed to a quite unphysical value, far away from the value well accepted by experiments. And we also see that strong correlations between G0 prime and G1 prime. So this kind of inclusion of G1 prime is now something quite good to do. And we also, in this figure, I show the weighted residuals for all the optimization schemes. And first, we see that we compare A and C. Or A and C, we see that they are kind of quite close with each other, which means that the introduction of G1 prime as a free parameter does not significantly reduce the errors. On the other hand, the introduction of GA kind of reduce some errors, but not at all the nuclei. Some nuclei are even performing worse with the introduction of GA as a free parameter. So this kind of thing tells us that maybe GA PCA should be calibrated at different for different nuclear regions with different values, which is something that's already done in other models like the shell model calculation. So also we noticed that errors are larger for nuclei with longer half-lives, and we know that these half-lives are sorted in the ascending order. And the physics reason is that they usually have a smaller Beta-Decay Q values for long-lived nuclei, and then one can derive that the corresponding phase space factors can produce greater theoretical errors. And also for those nuclei, the integral contour is smaller, so the number of poles inside is quite limited, and which may give us a large error as for short-lived nuclei. Errors of different poles may compensate with each other. And in the future work, we may consider assign different weights for short and long-lived nuclei, as their errors looks quite different, perform quite different. So, and another thing is that we see that the introduction of G1 prime as a free parameter is not something good, but we want to see this in a more concrete way, which is to use some kind of principal component analysis to determine the number of effective parameters in the calibration. The correlation can give us some indications, but that's maybe not enough. So to obtain a better understanding, we can perform the PCA on the normalized Jacobi matrix G delta, where this sigma is the standard deviation, and it's multiplied on it to make all the parameters have the same standard deviation after we do the transformation. So the PCA is basically done by the so-called singular value decomposition, and in this transformation, we can also obtain a new set of parameters through this matrix way V. And to determine the number of effective parameters, we can define the percentage of the variation, capital S, which calculates the percentage of the first squared singular values in the total sum of the square singular values, and it tells us the variation in data that the first M components can account for, and also the number of effective parameters is determined by some threshold number, which we take is here is 0.99%, and the number of effective parameters is the minimum, and that satisfies this threshold criterion. So then we can plot this cumulative fraction capital S in the 4 optimization schemes we have, and we see for A and B schemes A and B, all the parameters should be taken as effective parameters, while in C and D, like those zoomed in on the right panel, we see that basically the last two principal components should not be taken as effective parameters, and the number of effective parameters in C is basically 1, and in D is basically 2. So that means we know that C and D has the introduction of G1 prime, and well, yeah, the introduction of G1 prime as a free parameter is not good. It cannot be well calibrated. And now this ends my part for the chi-square optimization. And now let me give the stage to Mookyong for the Bayesian model calibration.
Hi everyone, my name is Mookyong-san, and I'm going to talk about Bayesian calibration of Beta-Decay calculation. So before I'm going to start, I'll briefly summarize what Tong just gave us to talk. So we're gonna have some physics model, it's a black box now, which takes in some non-inputs, P, it's a number of proton, number of neutron, and then some unknown calibration parameters. If we feed these into the model, we're gonna have some Beta-Decay rates and t-term. For now, we're not going to consider T1 prime based on what we just did. So how are we going to model this? The first step is we're going to have some field data. It's either GTR or the method. Just for now, I'm just going to consider one type of observables for these augmentations. Extension to different data types. Not very complicated because we're going to apply the same model to different data types. Independent. So the field data will be modeled. The first slide is computer model F, which takes in the non-input T and the calibration parameter X. And then we're gonna also assume some discrepancy term, which represent the discrepancy between this physics model to the reality. And then we're gonna assume some observational error, which follows normal zero with some sigma square. So we know what's at YF, we know what's at, we know what's the observation, but we don't know what delta is. So if there's no assumption, you can just choose delta such that it's model plus the discrepancy is the reality. Perfect. The first paper that approached this Bayesian calibration is by assuming this discrepancy using the Gaussian processes. So Gaussian processes, the easy way to think about this is infinite dimensional multivariate normal distribution. So if we have delta T1 to delta Tn, the finite number of this will follow multivariate normal distribution with some mean. In this case, we put the mean 0 and some covariance function is delta, and some comment. I'm just going to explain the Gaussian process in the next slide. So wait for a minute. And then if the evaluation of this computer model is not computationally expensive, what you can do is you can model directly the difference between the field model and the computer model, the receiver. If that's not the case, what we're going to do is we're going to approximate this F using the Gaussian process. So in that case, we're going to have another set of data called computer evaluations at some known inputs T, delta, and some X. So, right. So let's talk about some Gaussian processes. So Gaussian processes, it's again, it's infinite dimensional multivariate normal distribution. So statistical property are all based on the V function and the covariance function. But in the machine learning literature, the default is you're gonna normalize your outputs by subtracting the mean and divided by the standard deviation and applying the mean zero Gaussian process. It's like a default. So that's exactly what we did. So all the modeling assumption is based on the covariance function. And in our case, we chose the Matern class, which has the roughness parameter nu and the length space parameter L, where the K nu is a modified. So why we chose that covariance function is it's a wider class of covariance function, which includes squared exponential as a special case. So what I mean by that is, if you increase the roughness parameter from half to 3/2, 5/2, up to infinity, we can see that the covariance function actually converged from this blue to the orange, orange to the green, green to the red. So this red one, where the roughness parameter is infinity, is equal to the square exponential cone. And if you take a sample function coming from Gaussian process with each covariance function, we can see as we increase the roughness parameter, it was very wiggly, and then it changed to very smooth functions for extension. So when you model the physical processes, this smoothness assumption is not appropriate sometimes. And we had some issues when we use a squared explanation. Basically, the finite emulator performs worse than we do. So that's why we chose the Matern class. And we chose the roughness parameter fixed at 3/2, which is recommended in the machine learning. Okay, so now we have Gaussian process, and then another Gaussian process, and then the observation and normal distribution and the data. We're gonna estimate all of them. When I estimate a function, that means we're gonna estimate all the hyperparameters. So the natural way to do in Bayesian way is if there's any unknown, you're gonna put a prior on it and then estimate all together. So we're gonna call that integrated approach. We're gonna estimate all of them all together. This is the approach proposed by the original paper, but the issue is it takes too much time, first of all. For us, when we did a sampling, 10,000 sampling based on 2,000 compute evaluation and 29 experimental data, it took us 80 hours. This is not very efficient. Also, at the same time, if you do the interior approach, the fitted emulator sometimes is not very faithful to the computer simulation because we are feeding F and delta together to perform best for the field. So sometimes the performance of this fitted emulator is not good. Hence, some people approach this by modularizing this model. So what they mean by modularization is you're gonna fit the emulator first using the computer simulations. And then you're gonna do the estimation of the rest of the unknown. Why people use this is, first of all, by separating out these modules, you can keep preventing from unreasonably influenced by the field data, so that it guarantees the performance of the emulator. Also, by separating out these modules, can be viewed scientifically important. So it helps to understand what's really happening on the emulator, and eventually it'll help for the further research. Also, it's computationally cheaper because it's a step-by-step. Are we also gonna consider what happens if there's no discrepancy? There's no discrepancy. When we first do the Bayesian calibration, I discussed this Tong, and this was a first approach that he mentioned. So we're just gonna compare them, these three approaches, where the GA parameter is either fixed at 1 or not. So in total, we have 6 cases, right? All right, so next, I'm gonna now talk about some pi structure of the hyperparameter. So first of all, because of all the unknowns and their additive structure, there are some issues in the modeling, which is called identifiability. Basically, the calibration parameter is not identifiable. It means there could be 2 different values that make this model work. So how to mitigate this problem is a big issue in applying this model. One way to do is by setting the appropriate parameter space. We've been investigating a lot and we set it up the parameter space based on some physics knowledge. And also the other way to deal with this is the file structure. Mainly, these etas are the scale parameter in front of the covariance function. So it has nice interpretation. That is, it determines how much the variance of the target function coming from each term. Right? So what we want is the variance explained by the emulator is larger than the variance coming from the discrepancy term, and which is larger than the observation. So by setting this gamma like this, by changing this hyperparameter smaller and smaller, it stretched out to the bigger values. And by taking the inverse of it, we have we are expecting to be smaller and smaller on this term. So we have some kind of hierarchical order of the variance coming from this term, right? Also for the length scale parameters, theoretically it can have any positive values, but if you put a prior on the whole positive real values, then the sampling takes so much time. So we need some kind of reparameterization. That's what we did in here by taking the exponential of the order -4 so that it has a support between 0 and 1. So now it's perfect for a beta prior, which also has a support of 0, 1. And by setting up this hyperparameter values like this, the prior looks like this. All the masses are around 0, 1, saying that these landscape parameters have large values, meaning that the influence of this input to the output is small. So if they are important in the modeling, then the posterior, we're expecting the posterior to be moved to the 0. Okay. Okay, so those were the prior structure. Now let's take a look at the results. So first of all, said we're going to consider whether the GA is fixed or fixed at -1 or 3, right? So above these 3 is where the GA is 3, and below these 2 is where the GA is fixed at -1. And I represent the integral approach and the TTR and the Beta-Decay. So the first thing we notice is C0 prime has some multimodal issue. This is not what we want. There's some issues in the mixing. And one thing I need to mention is this black vertical line is the classical optimization. So this is 1.6, this is minus 1.1. So this, except for this C0 prime, this is also have wider standard deviation compared to the classical optimization. Others seem to work not bad. It has nice bell-shaped curve, which seems to converge in the posterior samples. But when you fix the GA, this is overestimate. Then what happens if we do approach using the modularization? So the first thing we notice is now we don't have multimodal, right? So we have nice mixing. And also the posterior GA has some uncertainty compared to the previous results. And it's when we did a chi-square optimization, the value was converted to 0.5. So this is more consistent with the chi-square result. And even if you fix the GA, the posterior seems to work nicely. Even if you have this bimodality in normal distribution. Next, what happens, there's no discrepancy. Oh, by the way, we use two different prior for the calibration parameter. One is a uniform prior for each parameter space. The other one is a truncate normal centered at the chi-square optimization results with some uncertainty. So this is like a weekly informative part. But the posterior seems to match each other in all the other cases. But in the no discrepancy case, the first thing we notice is when we fix the GA, the posterior seems very off from each other. On the other hand, if we free the GA, all of them have very nice fellowship